Hello? Yeah. You guys can see my screen? Okay. Let me just go here. Okay. Okay. So, 1 minute. Let me just speaker is off. Okay. Hello? Yeah, just 1 minute actually. There's like two voices. Okay. Okay. Welcome to week 2 of this PMRF TA session. Let me just check if this recording is done. Escape. Okay. Yeah. Sorry about it. Okay. So welcome to this week 2 of the PMRF TA session for the NPTEL course Approximate Methods in Quantum Chemistry. And so a brief intro of mine. So I am a PhD student, a PMRF fellow in the Solid State and Structure Chemistry Unit SSU at IIC Bangalore, and I am an NPTEL-PMRF TA for this course, Approximate Methods in Quantum Chemistry, and this is the second session of 8 2-hour interactive problem solving sessions, which happens every Saturday from 6 p.m. to 8 p.m. and it started on February 4 and until 25th March. So in today's session, we are going to solve some problem regarding the variational principle. Hello? Oh, 1 minute. There is still hello. Okay, now it's fine. This is incorporated. Please can't reduce it. Okay. So you guys are bachelor students or? Okay, you have completed. Okay, you have completed your masters. Okay. Okay, and so let's just start with the basics. So in this section, yeah, I'm going to talk about this like week 2 part, which was of variational principle. So first we will just start with 1 minute. Is there? Hello. Okay. There's no problem with my sound, right? Okay, no issue. Okay. Then just solve. Yes. Okay. So we have to first we are just going to prove the like basic thing. What is the like the proof that the energy obtained from variation is always greater than. So this has been done in the class itself, but let us just do it for the revision. So for the variational principle, as you know, basically we have to find this. We define. Instead of having an exact solution, what we have, okay, so we will take some, we will take some 5 which will be an estimate kind of our exact solution. Okay, so to do, so basically for that, let me just Okay. Let's do it. Okay. So uh, to, let's say we have a phi is our trial wave function. So we know that we will write it in this form, is h cap naught times phi divided by phi. Okay. Now this is just a uh, basic proof of that, which is kind of done in the class as well, I guess. So so what we can write is, we can write our phi wave function as a summation over I ci times psi of I. Now here psi of I are our eigenvectors of h cap. These are eigenvectors of h cap. Alright, so our ci is basically given by psi I phi. Okay, so from here we can write this as summation over I summation over j ci star cj psi I, okay, h cap naught psi j divided by summation over I summation over j ci star cj psi I psi j. Okay, so so I guess in the class yeah, I guess they were instead of writing this denominator and also like this this psi I psi j, since they are eigenvectors of this h, so we have this del ij. Okay, I don't want to reduce this. Okay, so what we can write here is okay, this h cap naught will act on this psi j, so we have summation I j ci star cj. So you what you will have is here ej psi I psi j divided by similarly summation over I summation over j ci star cj psi I psi j. Right, so so that will become del of ij, and thus you will get ci star ei divided by, this will be our summation of I ci star. Okay, so now in this case so we are solving for the ground state, that's why we have taken summation over I, complete all the i's. Now what I can do here is, I can show that I can do a plus E naught, which is the actual ground state, and minus E naught. Okay, and I can write this as summation of ci star ei, and keep this like this. Sorry. Now you can write this E naught summation of I ci star divided by summation of I ci star. Sorry, let's just keep this minus sign here, minus 1 here and plus E naught here. Okay, the E naught is a constant, and this summation over I summation I divide, they will just give you 1 basically, so it is E naught times 1. So this could be written as ci star ei minus E naught divided by summation of I ci star plus E naught. Okay, so here we can see that this value, this is always greater than equals to 0. Okay, so this is always greater than equals to 0, because I will go, because all the energy values, they are larger than E naught, ground state energy value, and then you have plus E naught as well. So overall this energy is greater than equals to E naught. So E phi is greater than equals to E naught. That is what is basically the variational principle gives you an upper bound on your ground state energy. Okay, so this was done in the class, but I guess like denominator also you can keep. You don't have to make it like they are, like your assumed wave function phi is normalized, even if it is not normalized. So we can do this. So this is just a similar way solution. Okay, now going to be 2. Let me just check once. Thing is gone. Sorry. Okay. 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 So next we saw this. Okay. Now this is also solved in the that lectures, but it was not like completely, I guess, solved. So we will do this as well for just for the uh, division. You can ask. You can also ask doubt from the assignment as well, assignment 2, because I will be covering just week 2 part, and I guess assignment 2 is that has been submitted already. So let us solve first this part. Okay, we have to derive the ground state energy and ground state wave function for one-dimensional simple harmonic oscillator using variational principle. Okay, now for 1D simple harmonic oscillator SHO. Okay, we know our Hamiltonian is given as minus h5 square by 2m. Let me just check once. There's no minus b square by dx square plus half m omega square x square. Okay, so this is your you can take this to be kinetic energy operator, and this is our potential energy operator. Okay, now to find the we have to assume our trial wave function, and so for the trial wave function we can here we will assume and since we so this is like as done in the class, we know that okay we know that the ground state wave function is going to be a Gaussian function. We will go with e to power minus lambda x square. Okay. Okay, yeah, just solve this one. So this is our guess. The lambda is our okay. Now to find this E phi, as we have the same thing, hk phi divided by phi. Okay. Now this will be equals to phi t cap phi plus phi b cap phi divided by phi. Okay. So these are basically the terms that we have to find the ground state energy. First we will find this phi, this thing that we will find, so we can write that here into minus into infinity e to the power minus lambda x square and e to the power minus lambda x square dx. Alright, so this will come as integration minus infinity to infinity to the power minus 2 lambda x square dx. Now this is equals to, this integral will be equal to under root pi by 2 lambda. So this is an important integral that comes a lot. It was, I guess, not shown in the class, like the calculations are not shown properly. So, but you can see that this integral is equals to under root pi by l. Okay. So this is an important integral that one should remember. So from here we have obtained our phi integral is equals to under root pi by 2 lambda. Alright. So this we have obtained. Okay. I can try. I guess I can show that this integral is infinity minus a x squared dx. Just wait a minute. Okay. Hello. Yeah. Okay. Sorry, actually, I just sorry, I missed some calculation something here. Okay, so this let's just solve. So what I'm going to here, like this is basically a solution, but I will show you how these integrals are actually being done, because this concept is simple, which was in the class as well, but what I'm trying to do is I will show you how this integral is done. So maybe what we want to show is this integral. Let's just prove this once, because these are important integrals and one should remember how they are derived. So basically we have this integral e power minus ax squared dx, and that integral we have used to find this phi. Alright, so let me just prove it. This is an a side, and a side I will show how this integral comes as under root phi by, because this is what we have basically used here. Okay, we have under root pi by 2 lambda because of this. Okay, so to solve this kind of integrals, what you do is you do an you say I equals to this integral, and you do an I square. That will be, you can write it as e power minus infinity e power minus a x square dx, e minus infinity to infinity e to the power minus a y square dy. Okay, so what we have is I square equals to, you can write this as minus infinity to infinity dx dy times e to the power minus a x square plus y square. Okay, yeah, you will have just this. Now to solve this, what we will do is we will do a transformation from Cartesian in the right direction. I have to do this. Okay. To solve this, we will do a transformation from Cartesian to polar coordinates. Alright, so what you do is, x square plus y square we consider at r square. Okay, so basically what we are trying to do is we have to go from dx dy to, we are trying to go into dr d theta to solve that integral, and for that we need this Jacobian x comma y by r comma theta. Alright, so this is basically the interesting part. So like the results are given in the lecture, but this is the calculation. So now here this Jacobian, how you write the Jacobian. So this will be x comma y by r comma theta. This is given by del x by del r and del y by del r, and this will be del x by del theta and del y by del theta. Right, let me just write it properly. Okay. Okay, these are del x by del r, del y by del r, del x by delta, and like x I will be written as r cos theta and y will be our r sin theta. So you can find this determinant. Okay, this is the equation that we are solving. Okay, we have to go from dx dy to dr d theta. Okay, I will put everything in one box at the end. So that if you solve this Jacobian, so x is r cos theta, that will be basically your cos theta, by r sin theta, that will be sin theta, x is again r cos theta, that will be minus r sin theta. Alright, and del y by del theta equals to r cos theta. Okay, and thus this will be equals to r cos square theta plus r sin square theta, which is basically your r. So this is your Jacobian. So this implies your Jacobian, which is given by x comma y r comma theta. This is the representation that is coming as r. Okay, so this implies I can write dx dy is equals to r dr d theta in this case. Okay, so this is how we find this Jacobian. Now let's come back to our integral, which was I square. Sorry, this is basically these calculations are important, so one should know like how these integrals are done once. Okay, I should have written it in different color maybe. Okay, let us draw a line here. So this is an aside. This is not the main solution. It's basically for your integral part, like how to solve that those kinds that integral. This is for regarding that integral part. So I will just keep it in one box so that no need. Okay, so and I will use green pen. Just using the pen. Okay, for this asides. Okay, so now we have I square. What we were solving, we had integration. So this was our I square. We have integration from minus infinity to infinity. We had dx dy dx dy times e to the power minus a x square plus y square. Now what we obtained from the Jacobian we will use now. So we will use I square integration. I will do it from minus infinity to infinity. I will write r dr d theta. Alright, and okay, let's just not put the limit right now, not minus infinity right now. Instead of that we write r dr theta, and it will be e to the power minus a r square. Okay, now the r will go from as you know, it will go from 0 to infinity. R could be 0 and infinity, and theta will go from 0 to 2 pi. Alright, so that basically gives us our integrals, and we have e to the minus a r square r dr and one integral 0 to 2 pi d theta. Alright, so we have I square equals to, this will give us 2 pi, and then what we will have is integration from 0 to infinity e to the power minus a r square r dr. Alright, now let this a r square r square equals to some alpha, so you will have 2ra dr equals to this d alpha. Okay, so this is a side, a side is in the box. Okay, so what we have here, basically we have a square 2 pi integration from 0 to infinity, it will be e to the power minus alpha d alpha divided by 2 okay, yeah, so we had rd, so instead of e to the power minus ar square we had e to the power minus r alpha, and instead of rdr we have what we have written, rdr is d alpha upon 2a. Alright, and 2 pi we already had, so our I square will be equals to, we can integrate this one, this is easy integration, let's put here e to the power minus alpha will just come to a minus alpha times minus divided by minus 1 from 0 to infinity, so e to the minus infinity is 0, minus plus is 1, but you get is pi by a. Alright, so we have derived, so that's why our integral I, which if you remember is minus infinity to infinity e to the power minus a x square dx, is coming as under root of pi by a. Okay, and this is the proof basically for that integral. So sorry, like this is a long proof, but it's important to like remember how this kind of integrals come along. Okay, so this is our aside. This is not a part of the solution, but this is how it is integral. You can either remember these integrals, or you can also you can see how to solve these integrals. Okay, so this is an aside. Okay, now let's just come back to our problem. So we use this integral I. Okay, since we have used this, since I is equals to, we have used under root pi by a, and here in the aside we have proved what we have used. So our phi will now become under root pi by 2 lambda. Okay, let's just go to the next part now. Now next what we need to find. we need to find our, let's say, phi v cap phi. So this is basically just integrations, but they are easy integrations actually. They are not that complicated that you have to obviously remember them. So we have e to the power minus lambda x square. Sorry, I will write it as half m omega square x square times e to the power minus lambda x square dx. Okay. Now I can take out half m omega square here common. Integration from minus infinity to infinity. Here we will have x square e to the power minus 2 lambda x square dx. Okay. Now now we need to find this integral. Okay, let's say this is our integral I1. Okay, so I will again use this green color so to find this I1 integral. Okay, now let's just go back to our I integral. What was our I integral? I integral, okay, or let's say, let us not go with the general thing. Okay, you can say like let I equals to this integral. Okay, e to the power minus 2 lambda x square only, not the x square term. Dx. This we know is given by under root pi by 2 lambda. Okay, this we have proved as well. So what we will do is, using this I integral, we will find this I1 integral that we need now. So what I will do is, I will do di by d lambda, right? That will be equals to d by d lambda. We have integral from minus infinity to infinity, and you have this e to the power minus 2 lambda x square dx. Now if you do this integral, okay, if you do this integral, okay, so here also I can write as this will be d by d lambda of under root pi by 2 lambda. And here I can bring this lambda differential here. So what I will get here is minus 2x square e to the power minus 2 lambda x square dx. Okay. So under root pi by 2 lambda. Okay, in this you have under minus 1 by 2, you will have minus 1 by 2. 1 by lambda to the power 3 by 2. This will be equals to, you can take minus 2 here. You will have integration minus infinity to infinity x square e to the power minus 2 lambda x square dx. Now if you remember, this is the integral where we got stuck when we were trying to find this v cap phi. This is our I1 integral, integration minus infinity x square e to the power minus 2 lambda x square dx. This is our integral I1 that we want to find. So by this we have found that our integral I1 will be 1 by 4 under root of pi by root 2 lambda to the power 3 by 2. Alright, so this is our I1 integral. So this is how we have found our integral again. So generally, if you remember that integral, I integral, then these then similar, by using similar techniques you can find this, like this I1 was also found from there. But these are easy integrals, like you should be able to solve them. So coming back to our problem where we left, we have half m omega square times our I1 integral. So our phi v cap phi will be equals to half m omega square I1 integral, which is 1 by 4, I can take 1 by 4 under root of pi plus this. Okay, let's write it in this form. 1 by 4 lambda under root pi by 2 lambda. I'm writing as you can see, our 5 we come under root pi by 2 lambda. So I need to cut from cancel from numerator and denominator at the end. So I'm writing this as under root pi by 2 lambda, 1 by 4 lambda, and we have our half m omega square. Right. Right. So this is also our this is all we have found. Now our remaining, which is our kinetic energy term. Find the kinetic energy term. This will be given by 2 minus infinity dx to the minus lambda x square minus hy square by 2m del square by del x square to the minus lambda x square. Right. So what we will have here? We will have minus hy square by 2m integration from minus infinity to infinity dx. Okay, so let us solve this. It is minus lambda x square okay, if you differentiate it, okay, you just differentiate it step by step. So if I differentiate it del by del x, integration this will be equals to minus 2 lambda x to the minus lambda x square. I'm also actually doing it right now only, so that's why this takes time, because the calculations will take time. And then you solve completely minus 2 lambda x to minus lambda x square. Alright. Okay, let's just solve this completely. So we will have minus infinity, we got dx to minus lambda x square. Now let us solve this differentiation. Again you differentiate one time, minus 2 lambda to minus lambda x square, and then you will have plus, you will have 4 lambda square. Right. You will have 4 lambda square x square to a minus lambda x square. Alright. Now we will again have some integrals. Alright, let me just write it like this, and you can take minus 2 lambda here, integration from minus infinity to infinity will be e to the minus 2 lambda x square dx. Okay, so we have minus 2 lambda d to minus infinity to the minus 2 lambda x square dx, and here from here we get 4 lambda square to come out. We have integration from minus infinity to infinity x square. Again we will have e to the minus 2 lambda x square dx. Right. So again we have some big integrals. Now this integral we know we have Actually, we have solved both the integrals. If you see, this is our integral I. Let me just this is our integral I that we solved, and this is our previous integral I1. If you remember, these are those two integrals. So I can just use that thing. So I will just use that 1h square by 2m minus 2 lambda. This will come under root pi by 2. Okay. This is our e minus ax square under root pi by 2 lambda. Okay. Now plus we will have 4 lambda square, and this is our x square e to the power minus 2 lambda x square. And let me just see the I1. That is the integral integration minus infinity x square to the minus 2 lambda x square dx. That is what we have, integration minus infinity x square to the minus 2 lambda x square dx. So that integral comes as 1 by 4. 1 by 4. I'm sorry, 1 by 4 lambda under root pi by 2 lambda again. It was that. Alright. So this is what we have. So finally we have our 585. That will be equals to, let me just keep this one h5 square by 2m common, and I will also take on pi by 2 lambda times minus 2 lambda okay, minus 2 lambda, and here I will have 4 lambda or just lambda. Oh, we just have lambda. So our this is coming okay, I guess. It will become hy square by 2m lambda under root pi by 2 lambda. Alright. Oh. So let me just check this once if we are on the right side here. We are on the right track. Okay. So we are almost done now. So I can first write this phi hk phi. Okay, we started with this thing. We have to find this thing. We have to find these three things. E5, to find the E5. After doing this integral, you can write the direct answer, or you can see that these integrals are also not that tough. You can actually solve these integrals. Phi, vk phi. Let me just write this. This is will come as hy square lambda by 2m plus, if we go with phi vk phi, which is half m omega square times 1 upon 4 lambda times under root pi by 2 lambda. Correct. Alright, so this is our hk phi. Let me just write it again. H square lambda upon 2m from the kinetic energy, and we will have 1 by 8 m omega square by lambda on the potential energy times under root pi by 2 lambda. Right? So our E of phi, then it goes to phi hk phi divided by phi phi. Now as you can see, we have under root pi by 2 lambda, and our phi phi was also under root pi by 2 lambda. Okay, so that's why I took out those things common. And E5 finally we have H5 square lambda divided by 2m plus 1 by 8 m omega square by m. Alright, now using the variational principle, now the steps are much easier. It was basically this question I just solved mainly to show you how the integrals are done. The integral, because they are very common integral in physics, and it's especially at I integral, that we can minus infinity to minus ax square dx. So you can remember it, and you can see that these are easy. And I guess the main part that we have learned new is this how this Jacobian thing is used to solve this I integral. So that's important. Right. Alright. Just do this d5 by d lambda. Right. This we have to do 0. We will have h5 square by 2m. Right. Plus 1 by 8 m omega square and minus 1 by lambda square. That is to be equals to 0. So what we have is h1 square by 2m equals to 1 by 8 m omega square 1 by lambda square. So lambda, so let's say our lambda min, or let us go with whatever lambda we are solving. Okay, let us say it to be lambda min. So that will be equals to h1 square by 2m times 8 upon m omega square. So our lambda min omega square before h5 square by m square omega square. Okay. Okay, sorry, I guess I did some mistake. Sorry about it. Like there is some calculation mistake actually. Just write it again. M square divided 1 by 8 and omega square, and we will have 2m square, right? Lambda square will go there, 2m by h square. Alright. So we will have m omega by h cross whole square, m omega by 2h cross whole square, lambda mean square. So our lambda mean, I guess now it is coming to 4 m square minus, okay, yeah. So we can write it as m omega by 2h cross. Yeah. Okay. So there could be, I guess we might, there could be, you can say like plus minus m omega by 2h cross, but you can check it, like you can this is the lambda min that we will get from the variational principle. You can, if you want to check, you can do double derivative of the energy and see that this will give you a minimum result. Alright, so we have this value. Now we just need to find our ground state energy E5, okay, at lambda min. So as you remember, okay, this is our E5. Our E5 will be equals to now h5 square lambda min. Here we have divided by 2m plus 1 by 8 m omega square by lambda min. Alright. Alright, so let's just put our lambda min here. whole square by 2m will be m omega by 2h cross plus 1 by 8 we have m omega square, and this will be m omega by 2h cross, right? So we can write this will be half, and we will have is like this we have 1 by 2, right? We have 1 by 4 h cross omega plus here also you can see okay, let us cancel, let me just show you. Just do this thing here. Okay, so mm will cancel out, h cross will cancel out, so you can see this, and this will cancel out, this omega will cancel out with this, so I hope this is easy. H cross omega, so basically what we are getting our E phi finally that we are getting is half h cross omega, and that is our E naught value as well, that is the ground state energy that we have obtained. Alright, now similarly now what will be our phi, our wave function phi that we are talking about. So phi, what we have assumed, basically we have assumed it to be some e to the power minus lambda x square. Okay, this was our phi, this we have assumed, this is our trial wave function, should have written it here, sorry, this is our trial wave function. Alright, so and then we did all the calculations, right? Now I will put a normalization constant here, e to the power minus lambda here m omega by 2h cross times x square. Okay, now to find this for the sake of completion, we have to normalize this phi, this has to be equals to 1, right? So this integral minus infinity to infinity you have to take again, e square e to the power minus m omega by h cross x square dx is equals to 1. Now this is the this is basically the same integral, if you remember. So this thing will just again we are encountering the same integral e by minus ax square dx integral, right? So this integral comes a lot. So it's good to remember this integral as well, because it just comes a lot. So it is equals to under root pi by a. So under root pi by m omega h cross 1, or your normalization constant a is basically equals to m omega by pi h cross to the power 1 by 4. Because we have to normalize our trial wave function as well. That's why we have done. Okay, we have to normalize. This is the normalization. Normalization constant. All right. So that's why we did, and finally we have our wave function also. So this is in this example, basically our wave function works because we obtained our exact ground state wave function. We got our exact ground state energies. Okay, this is how we have solved our this problem. All right, let's go to another problem now. Okay, so This is an interesting. So this is the problem of linear variational principle. So the previous problem was actually like might have been solved in the classroom, but the integrals so integrals are also very easy to do. So mainly we did those someone's let me just stop sharing so maybe there's some problem. Correct. Okay, I guess there was some problem with sharing screen. Okay. So okay, now we will do this problem number 3. So this is regarding this linear variation principle that you might have learned. So in variation principle, we can take one kind of trial wave function, and we can put one parameter. Okay, but as you might see in the lecture, this is just like it gives a good approximation for the energy, but basically it depends on your trial wave function. So to get the properties for the wave function or percent wave function, you can use linear variation principle. Here you have basically some wave functions, how they act, and for your actual result, what you will do is that by you can have some sort of idea that by combining two kind of wave function. Excuse me. I guess there is some problem. Just share my screen. Okay, yeah. Sorry about that. Yes. Okay. So, so in this one also we are going to see some similar kind of example, like how linear variation principle can help us. It's a better way to understand it, especially for the wave functions. So, like what we have to do is using linear variation principle, it will define the difference between the valence orbit of hydrogen atom when the center of mass is taken approximately to the nucleus. We will call it like H case, and our actual case A case when center of mass is between the nucleus and the electron. So what I'm saying is, let's say you have, let us use this pen. Okay, let's say you have your nucleus, okay, and you have, this is your Mn, and you have your electron here, right? This is some Me. So the generally what we do is the exact center of mass must come as here. But since we know that this Mn is approximately 1836 times of Me, so it is very high, so we can take it to be very high, and we can assume that our center of mass is actually is at the core. Okay, and that's how we solve our for the hydrogen atom we can solve our 1s orbitals and all. So this is our exact center of mass, okay, and this will be our actual case A, that I'm saying A case, okay. Or we can approximate our center of mass here, approximate center of mass. If we take mn to infinity, if we are taking that, this is very big, and this is our hypothetical, we can say this is not the exact H case, right? So basically what we do is, when you have to solve, you will use the reduced mass, which is given by 1 by mn plus 1 by me. Okay, now in your actual case, this reduced mass must come as mn plus me, because your center of mass is between the nucleus and the atom, while you are in your hypothetical case, this will just come as me. Okay, because you can see that since mn is very high, so 1 by nu h will be approximately equals to 1 by mn, because mn is very large. Alright, so this is the case, and what basically we are saying is to understand this, how our 1sh in this hypothetical case, our 1s orbital, if we consider that our like we have our center of mass at the nucleus itself, and our electron is revolving around, how is it different? How this kind of 1s or 2sh orbitals are different from our actual case of 1sa and let's say 2sa orbitals. Our s orbitals, how our s orbitals might change. Okay, so before going into variational principle, what we will do, let's just think about it in a slightly different way. That's why I'm writing in word. So now we know. So basically, instead of solving directly with variation wheels, let's just first try to understand like what could be the result. What we would expect. So we know that this nu A is lighter than this nu H. Okay, because you can see that this nu H is just equals to your me, while your mu A is basically mn divided by mn plus me times me, and this value is less than 1. Alright, so that's why you know that mu A is less than mu H. Alright, now to check the settings are okay. Right. Now, if you like recall, you must have been told that okay, this is our bore radius. AB is given by 4 pi epsilon naught h phi square. This is given nu by e square. Okay. And such that we know that our 1s orbital basically, let's say approximately, you can write it as just e to the power minus r upon ab. Right? Now, if our hello, I guess it's working, right? Hello. So if our nu is lighter, okay, so what will happen here is our bore radius, as you can see, AB will be on this side. This is our bore radius. So our AB is going to be larger, alright, because AB is inversely proportional to mu. So what will happen because of this? What we'll have is our function which is e to the minus r upon AB. Since AB is larger, so this function will decay slowly. And what does this mean? This means I would expect my psi1s of actual case, which actual case where my nu is actually not just the it means it is not the electronic mass, it is the this reduced mass. It will be more diffused. Alright. Okay, and we will see this through variational principle. We will see this through variation method. Right. Okay, so basically more diffuse, it means that okay, if you remember you have 1s of a orbital, not the probability distribution. So let's say this is your 1s of a, the 1s of hypothetical. This is your 1s hypothetical, right? So your what we am saying is that what you will observe, this will be more diffused and it will go higher value. So this will be your 1s of actual case. Okay, this is your actual case and this is your hypothetical. So it will be more. So and you can understand, like a particle which is more lighter, it can go away from the nucleus more easily. Alright. So this is what we will prove from the variational principle. Right now we just understood this thing, what our problem is, and yes, we can kind of solve it. And now we will try to understand it, how to actually prove it using the variational principle. Now, from there, from all this discussion, we can get one idea that our 1s orbital, actual orbital that we are talking about, we have to we need to keep the symmetry, spherical symmetry, and at the same time we want more diffusion. Basically, we want our actual wave function to be more diffused. So one combination that will directly come to your mind, that should be like okay, it should have 1s of hypothetical, 1s orbital, and what will be the same symmetrical kind, spherical symmetric wave function with more diffused. So best bet would be using side 2s of h, which will be more diffused. Alright, so this will be our wave function. I am writing in psi 1. This is our basically this is our triad wave function. This is our triad wave function. Okay. Alright. Now, okay. Now, if you remember, we have to find this Hamiltonian matrix. Okay. Now we have to find this Hamiltonian matrix. Now we have to find this Hamiltonian matrix. Okay. Hello. Hello. I'm just sorry about that. I just have to check technically. Hello. Is working. Hello. 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 Okay. So what we have here is, so okay. So for this linear variation principle, we know that we have to solve something like a secular determinant. If you remember, basically we will have an H matrix minus our assumption of E tilde, whatever our energy values are going to be, times the S matrix is the overall matrix. This we have to find this kind of equation, and This is sacral. This is called sacral determinant. All right. This is what we have to solve. Okay, so H will be given by psi 1s of H times H cap. Remember this H cap is actually our actual Hamiltonian. So okay, let us solve something that is easier first. So we know that this S is our overlap matrix, and since psi 1s of H and psi 2s of H are eigenvectors of H cap hypothetical. Okay, this is the hypothetical one, which has basically minus h5 square by 2m e, or you can say new hypothetical. This is the new hypothetical del square minus ze square upon 4 pi epsilon naught r. Okay, this is not our actual, this is the hypothetical. H case Hamiltonian. So these are the eigenvectors of this H case Hamiltonian, and what we have to solve it for the exact Hamiltonian. So this will be our HE. This will be our actual case. But since these are our eigenvectors, so what we have is here is that our S matrix, which is equals to psi 1s of H, psi 1s of H, our eigenvectors. Basically what we have is psi 1s of H, psi 1s of H equals to 1, psi 2s of H, psi 2s of H, that is equals to 1, and this will and what we have psi 1s of H, psi 2s of H, that is equals to 0. Alright, so our S matrix, which is given by psi 1s of H, psi 1s of H, psi 1s of H, psi 2s of H, psi 2s of H, psi 1s of H, psi 2s of H, psi 2s of H. This you can see will be equals to 1, 0, 0, 1 identity matrix. Alright. So this is something that we have obtained. Now, next we want to obtain this H matrix, HA matrix, which will be given by psi 1s of H, H cap of A, psi 1s of H, psi 1s of H, H cap of A, psi 2s of H, psi 2s of H, H cap of A, psi 2s of H, psi 2s of H, H cap of A, psi 2s of H. Now here H cap of A is actually minus h5 square by 2 nu A times del square minus E square upon, I guess I have written it somewhere. No, they're not need to, but it's Z, we are talking about hydrogen atoms, so Z will be 1. Like that. We have 4 pi epsilon naught R. Okay, so note is important. 1s of h and psi 2s of h are not the eigenvectors of h cap of A. Okay, whatever our h cap, because we have approximated, here we are trying to find the ground state eigenvector for this h cap of A, which is 1s of A, our tri-wave function, and they are 1s and 2s are not the eigenvectors. So just a disclaimer kind of. Okay, now now we know this psi 1s of h. We need to solve this integral, and let's just write this integrals h in the form of, okay, this you can write h as h11, h12, h21 and h22 as well, and write it in shorthand notation. Okay, now here we have psi 1s of h is given by 1 by pi by A naught is here, that is your pore radius basically, A naught q AB cube to the power 1 by 2 e to the power minus r upon AB. AB is your pore radius, and psi 2s of h is equals to 1 upon 32 pi AB of q 1 by 2 minus r by AB e to the power minus r upon 2a. Right. Okay, so these are our wave function, and using this we will find our h11 and h22 everything. So h11, so which now these will be set. Okay, so this will be some these are going to be actually just integrals, and I can give the values, but that is I guess not basically you have to just like this will be psi 1 star times your h cap of A psi 1s star d tau, and your tau is basically equals to r square dr sin theta d theta d phi, and you just have to integrate with respect to r only, because psi 1s and all these things just depends on that only. Okay, similarly we will have your h22 as well, psi 2s star d tau, and h12 equals to h21 sin 1s star h cap of A psi 2s star d tau. Right. So I have the value with me. So these are R actually. Okay, so if you do this calculation, you have this wave functions, and you just have to do this integrals. So if you find the values, then the values will come as gamma minus 1 h square upon 2ab square times m of E. Okay, this will be h11 h22 this one 4 gamma minus 1 h phi square upon 2 ab square by me, and we have h into h2 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 16 gamma 7 times 2 to the power 1 by 2 h phi square by 2 ab square and me. Right, where gamma is equals to basically me by m, right? So this is basically what will be the integration. So this is integration part, so I am just ignoring it here. Main is that basically what we will do is we will solve our this integral, which is h minus e tilde s, our second determinant. This you can write it as h11, h12, h2, 21, h22 minus e tilde. E tilde is our energy, you see the energy value that you will get, and here we will have S11, S12, S2, S21 and S22. From this you can get this equation H11 minus E tilde times S11, H12 minus E tilde times S12, and H21 minus E tilde times S21, and H22 minus E tilde times S22 is equals to 0. So continuing like this, and when we know our S matrix, it was an identity matrix, so we have H11 minus E tilde, we will have H12 here, H21 here, and H22 minus E tilde equals to 0. So from this one, we just have to open this determinant, H11 minus E tilde times H22 minus E tilde minus H12 and H21 equals to 0, and H1 plus H21 are going to be same, and if we open this integration, this so this will give us an quadratic equation. E tilde square minus H11 plus H22 times E tilde plus H11 H22 minus H12 and H21 equals to 0. Okay. Now we have this H11, H22. Let me just check once. Okay. Yeah. So this is what we get, the quadratic equation that we get, and the lowest root, if you calculate. So, and you have to put this H11, H12 values that we have obtained. So that is just the calculation part. So let me just write it for the computation only. Just not doesn't be too much computation. And this will be equals to 8 times, again we will have seen gamma minus 1 times 5 plus 3 something 1 plus 2 capital gamma square to the power 1 by 2 times h5 square by 2 ab square and e. So basically this is just calculation for the completeness sake. I have written what this E tilde is going to be, and where this capital gamma will come as 2 to the power 6 times gamma 3 to the power 4 gamma minus 1. Right. So for the completeness sake, basically you will get this lowest root, okay, and this gamma is equals to me by mn. Alright, so basically what you can see is that this E tilde in the end will come as minus 0.99946 times this thing, which is h5 square upon 2ab square. Alright, so E tilde will be something like this, and then using this root we have to find our equations. So as you might know, our equation will come minus, it will be h11 minus E tilde h12 h21 h22 minus E tilde times c1 c2 equals to 0. So using the E tilde value that we will have two equations, h11 minus E tilde times c1 plus h12 times c2 equals to 0. Another equation will be alright. So this will be the equation that we will get, and this is one equation we will get from our matrix, this matrix equation here, and one we can get h21 c1 plus c2 times h22 minus E tilde. Alright, okay. So and also for the and we want our tri-wave function to be normalized as well. For this we have c1 square plus c2 square equals to 1. This is also you can put the tri-wave function to be normalized. So when on solving all these three equations, basically for your particular this E tilde that we have obtained, so you can check these calculations, but they are like too complicated, basically what you will obtain is c1 equals to 1 and c2 equals to minus 5 minus 4. This will be our result. Now this is the interesting part finally, that we are getting our answer. So our psi 1s of A is coming as psi 1s of H minus 5.4 into 10 to the power minus 4 times psi 2s of H. Okay, so this is our final actual ground state from this wave function. Now that's the that's an interesting part that we are seeing. So what we are seeing here is that this site okay, since our actual ground wave function is basically the 1s of h, the hypothetical 1s, minus whatever you are in the hypothetical case means your center of mass is at the nucleus. So it is minus something from the side 2s of h, which is more spread out. So this gives you a slight reduction in amplitude. This gives you a slight reduction in amplitude. At r equals to 0. Okay, and since you have psi 1s of A at r equals to 0 equals to psi 1s of this hypothetical at r equals to 0 minus some epsilon, which is a small value, psi 2s of h at r equals to 0. Alright, so from here we can see, okay, so we just by looking at these if you in the start, just by without variation principle, first we started with this thing and we analyzed what this center of mass and everything could lead to, and using variation principle also we are getting the similar thing, like we are getting that our wave function is actually having lesser amplitude direction and thus it will have more spread. So small mix, what we can say is that small mixing with US of psi 2s of h gives an actual H atom 1s orbital. So we are able to obtain it, and that is what we have and why this is working, because we know that a lighter nu has more freedom to move away from the nucleus. So since we already knew that this should happen, that there will be more dispersion from all this radiation, so what we found is that by R, okay, so since we know that there will be more diffusion, that's why there is a reduction also that you can see here, that r equals to 0 there will be a reduction, and that's why there will be more dispersion in the actual case. So it will decay slowly. Okay, that's why our actual wave function will decay slowly. Lighter nu has more freedom to move away from the nucleus, and so we obtain the same thing from the variation principle as well. Now let's just go to our next problem. Okay, now in this problem we will do the same for the, we will take a trial wave function e to the power minus lambda r and apply the variation of plots for the hydrogen ground state to find this whatever this lambda value is going to be. Now as you can assume as well, okay, so this kind of problem was also done in the in your lecture, and there you might have used some wrong variation of wave function, but here you can see, okay, the wave function that we assume is actually, since we know that our 1s orbital, we know that it's approximately e to the power minus lambda upon e to the power minus r upon ab. So we have a good functional form. So using variation principle, what you will found is that we will get the similar lambda values. Right. All right. So let's just start this. Okay. So we will start with our wave function, our Hamiltonian. So our Hamiltonian h cap is written as so our Hamiltonian h cap I can write as minus h pi square by 2 nu. I'm using nu here, the reduced mass. So this is the actual case, times radiant square minus, let's say we are talking about the hydrogen atoms, z will be 1, e square upon 4 pi epsilon r. Okay. And our trial wave function psi that we have taken e to the power minus lambda r, this is our trial wave function. Alright. So in this case, since now we only have this r value only, so what I can take this is delta square psi. We will just have the we just have to take care of it. Okay, so like the delta square will open, as we know, this delta square will open as 1 by r del square by del r square times r plus 1 by r square h by square and k square. Alright, but since we already have radial contribution in wave function, we can simplify our del square to just 1 by r. Sorry about that. Okay, so it will be just equals to this will just be equal to 1 by r del square by del r square r. So this only way we need to take care of, right? So what does this this means that our del square psi, I can just write it as 1 by r del square by del r square of r times psi. right? So let's come back to this. Our E5, again going with the same procedure, it will be phi h cap phi. I have taken it to psi actually, because it is phi. Or I just go with psi only. Because okay, here let me just write this as my E tilde instead of this notation. So E tilde is equals to psi h cap psi divided by psi psi. So what are the integrals that we are going to get? First we will need to find, let us start with psi psi. Now that will be equals to our psi star of digits of r, psi of r, d tau. Now d tau will be equals to r square dr sin theta d theta d phi. Right. And so now I can take this d phi. D phi integral will be from 0 to 2 pi, and psi r will have no theta dependence, as we have said earlier. It is, and this will be, theta will be from 0 to pi sin theta d theta. Right. And we will have integration from 0 to infinity. I will just, let me just write it right now as, okay, psi r we have written like this, e to the minus lambda r. So this is e to the minus 2 lambda r square dr. Alright. So again we will have some integral, it will be equals to 2 pi. Now sin theta d theta, if you integrate, that will be equals to minus of cos theta from 0 to pi. Right. And this integrate over minus 2 lambda r square dr. Okay, now we can integrate it. Okay, so I guess we are already quite late. Okay, so here I am not solving the integral. You can check that this integral becomes as 1 by 4 lambda cube. Alright, and this will come as 2 pi times 2 to 4 by lambda cube. Because of constraint time I have to no, I am not you can check this integrals are easy, similar technique that we used in that harmonic oscillator stuff. So these integrals also you can try to find out. This integral you can solve, I guess, actually by integration by parts. So solve by integration by parts. Integration by parts, if you try, which is basically integration of here u and d prime. It is equals to ub limit, whatever limits here, minus integration to u prime v. Okay. So using this, this could be solved. You have to take v to be your r square, right? You will take your you will take u to be your r square and v to be your this. Okay. Let's just okay. So basically, this will give you your first term, which is psi. This psi get psi, that will be equals to from here pi by omega cube. This is our calculation that we have obtained. Right. Similarly, what else do we need to solve? Now, from the potential agita, okay, let's say this is our within this is our kinetic energy T cap. Again, this was our potential energy V cap. So we use from this now psi V cap psi. This is basically given by psi T cap psi. Similarly, psi V cap psi. Right. So to solve this, you will have your integral psi star of r, and your v cap is basically minus e square upon 4 pi epsilon naught, which is a constant, times 1 by r psi of r d tau, bracket d tau. Alright, now we can take this constant, epsilon naught, half of epsilon naught, integration. What this psi star r, then I have this psi star e to the minus lambda r times I will have 1 by r minus lambda r plus r dr sin theta d theta d phi. Again, similar what we have solved earlier for pi epsilon naught. There is no theta dependence, so we have 0 to 2 pi d phi, condition 0 to pi d theta, and then we have 0 to infinity. This time we will have r times e to the power minus lambda r dr. Minus 2 lambda r dr. Right. So on solving this, what you will get is this will be minus e square upon 4 pi epsilon naught, whatever your constant. Okay. This will again give you 2 pi. We have a sin theta d theta, which will give you 2 again. And this integral, if you solve, will give you 1 by 4 lambda square. Earlier I thought we have 1 by 4 lambda cube, this will give you 1 by 4 lambda square. So from this we have obtained our another term, which is psi v cap psi is equals to minus e square upon 4 pi epsilon naught I have already square. Okay. Now last part we saw for psi t cap psi is the kinetic energy part. So here also we have this psi star. This function psi star r is this function of r. This function is minus h square by 2 we will have your del square psi of r theta. I will take minus h square by 2 nu outside. This is a constant, and we will have our psi square of r del square psi of r theta. And as we discussed, since we will just take this del square psi is equals to 1 by r del by del r square r psi. So that will become minus h square by 2 nu psi star of r. I will take it as 1 by r del square r del r square times psi of r, and theta will be our r square dr sin theta d theta d phi, right? So let's try to new. Now we will do again that the theta parts as always, it is 0 to 2 pi d phi. Sin theta d theta. Okay, we know what these values are going to be. Now we will solve this equation for 0 to infinity. So what we'll have here is if you solve this, it will be minus lambda r, okay, by r will be here, and we have to differentiate del square by del r square times psi of r, which will open as del square by del r square times r, it will be minus lambda r times r square dr. Correct. So here I will minus h square by 2 nu. This will be simply 2 pi, and this will be equals to 2. And in this integral, is integration from 0 to infinity to minus lambda r by r del by del r also. Now this integral we have to continue. Okay. Now, so basically, what you will get here will be two integrals. One will be equals to we'll have lambda square times 0 to infinity, but we will have this e to the power minus lambda r, e to the power minus 2 lambda r, 2 minus 2 lambda r times r square dr, and 1 will be equals to minus 2 lambda times integration same 0 to infinity, minus 2 lambda r dr, right. So this will be the two integrals that one has to solve, right. And when you will solve, if you solve this, then you will get something again yeah, so we have solved this integral, if you remember, in our previous let us write them actually. We have, I guess, both the integral we have solved earlier as well. So you can see it is similar to what we did in that calculation as well. So this integral leads 0 to infinity minus 2 lambda r square dr. This will come as 1 upon 4 lambda cube, right? And then we have 2 lambda times this integral, so it will become minus 2 lambda dr is 1 by 4 lambda square. So what we have here is minus h square by 2 times 4 pi times 1 by 4 lambda minus 1 by 2 lambda. So by calculation, what we are getting is 4 pi times minus 1 by 4 lambda. So finally we have our result. It took some time, but like this we have the result. H5 square, you can see it's we have this 4 we cancel out, this minus 1 and it will become plus. You will have h5 square pi divided by 2 new lambda. Alright, so this is our finally psi t cap h caps. Okay, so now we are almost done with our variational this problem. So let's go back to our unit we're trying to find. Okay, so we have to do this e, we have to find this e tilde, and we are almost done. So our e tilde, we know as psi h cap psi divided by psi, that will become as psi t cap psi plus psi v cap psi divided by psi. Now we will just put our values. So this was our h5 square pi upon 2 new lambda plus we have psi v cap psi, which is minus e square upon 4 pi epsilon naught, e square upon 4 pi epsilon naught pi by lambda square. Divided by our psi wave function, which is pi by lambda cube. So So our E tilde finally comes as okay. So if you divide if you do this, okay, so we become lambda square h square by 2 nu minus e square lambda upon 4 pi epsilon naught. Alright, so this is our E tilde. We have obtained our E tilde. And for the variational principle now we have to do d E lambda by d lambda equals to 0. Okay. To find our variational parameter finally. So there we will have lambda h phi square by nu minus e square upon 4 pi epsilon naught. That has to be equals to 0. That gives us lambda equals to nu e square upon 4 pi epsilon naught h phi square. Right, and if you remember our bore radius is equals to 4 pi epsilon naught h phi square by nu e square. So if you remember that problem that we have previously done for the problem number 3, so from there we defined this bore radius. So basically our lambda is coming as 1 upon AB, and this is our solution for radiation principle. So we want to find this ground state energy, and lambda is coming as 1 upon AB, and so our wave function psi is what we without the normalization constant. Okay, so it will e to power minus lambda upon AP, which is our psi is coming as let me just write it as something this times A, and this A is some normalization constant. I'm not normalizing it now, but we can normalize our wave function normalization constant. So you can see that this is exactly our exactly ground state minus capital ground state minus orbital that we are getting, and our energy also I can write our energy E tilde. Okay, that will be equals to what? Lambda equals to that lambda mean. We can write it as lambda mean actually. Mean that will just come in lambda mean square by h square by 2 minus e square lambda mean upon 4 pi epsilon naught okay, and let's just put what our lambda mean is actually 1 upon AP, or I can just put the actual value, then you will see that what we are getting is actually the actual ground state energy value as well. So it will be nu epsilon nu e square upon 4 pi epsilon naught h square whole square h square by 2 nu minus E square upon 4 pi epsilon mu E square upon 4 pi epsilon H square. And if we do some cancelling here, there is do some cancelling here. So I can't show it. Okay, that is nu square to the power 4 upon 4 pi epsilon naught 4 square h pi to the power 4 h pi square upon 2 nu minus E square upon 4 pi epsilon naught whole square mu E square upon h pi square. And I can show some cancelling. This will be cancelled out. This next square will cancel out and we will get 2. So we will get basically e to the power 4 upon 4 pi epsilon naught h phi whole square divided by 2 minus e to the power 4, and there will be this one e to the power 4 upon 4 pi epsilon naught h phi whole square, and thus our E tilde will come as minus nu e to the power 4 upon 32 pi square epsilon naught square h phi square. And this you can check is our actual ground state energy. Ground state energy for hydrogen atom, or okay, or the energy of an s orbital, or actual ground state energy actually was electricity. Okay, so basically with the help of radiation principle we were able to find our electric ground state 1s orbital, and we were also able to find our actual ground state energy as well. Okay, so we have solved this problem as well. Okay, so our time is also over now. Okay, so hopefully, so basically we have we started with the basic revision of variational principle. Then in question number 2, just a quick revision actually, so what we did in today's class. So basically we just first went to this normal variational principle result. Okay, that the whatever energy we get, it gives you an upper bound on your actual ground state energy. Then we went to problem number 2, in which we did for the 1D harmonic oscillator. Mainly we were able to understand this integrals, which was important, and then we saw this similar manner in which this is solved. We have to solve the variation principle problem, which main is this in I guess in this problem was this integral. Then in problem number 3, we basically went to this linear variational principle problem, and we understand that for an actual hydrogen atom, with the help, if we know the form of the wave functions for this hypothetical case of when its center of mass is not exact, but we are approximating it to the nucleus, then how we can obtain from there our actual 1s orbitals, the hydrogen, and we found that they will be more dispersed, like which we could understand from our discussion about this reduced mass. And then we did this our variational principle, linear variational principle, and we obtained that okay, our 1s actual orbital, we can get the actual 1s orbital by just mixing the 2s of our hypothetical orbital with our 1s orbital. So here our linear variational principle is useful. And then in the last question, we basically solved it for our variational principle for to find the hydrogen ground state, hydrogen atom ground state, and there also we were able to find since we went with the exact form, our trial wave function was quite correct. So we obtained our exact ground state 1s orbiter and the ground state energies. Okay, let me just stop sharing. And thank you for your time.